The Poisson distribution. The Poisson distribution. This is going to be a little bit of a different type of process than something we've encountered before. If you think about how the hypergeometric distribution and the binomial distribution, negative binomial distribution are all, they have some similarities in terms of the type of experiments that they would be involved with. The Poisson distribution is going to be a little bit different for us here. Okay, so what does a Poisson random variable do? A Poisson random variable counts the number of events occurring in a fixed interval of time. So this is really about counting. Counts the number of events occurring in a fixed interval of time or space. Counts the number of events occurring in a fixed interval of time or space. In a fixed interval of time or space, if these events are occurring at a known constant rate and independently of the time since the last event. All right? If these events are occurring at a known constant rate, and independently of the time since the last event. Independently of the time since the last event. Okay? Independently since the time of the last event is kind of important in terms of like an actual practical application of a Poisson random variable. So independent from the time since the last event. Sort of like, Poisson is French. This is named after the origins involve like counting the number of fish. I believe Poisson is French for fish or something close to that. And so you might think about if you've ever gone like fishing on a lake, that the number of fish you catch in any hour is independent of the time since the last event. So if I catch one fish, most fishermen actually assume that it's not a Poisson process because they think that might be a hotspot. So if two people keep catching fish, they're going to go to the same location. That's not really independent in that sense, right? It's sort of like just because I catch one fish here in this specific location doesn't mean I'm any more likely to be catching more fish in this specific location. You want to be independent from the time since the last event. So a common example that we'll look at to kind of help wrap our heads around this would maybe be something like the number of telephone calls received per hour by an office. Number of telephone calls received per hour by an office. All right. And in this sense, we'd assume if in a particular hour an office got 10 phone calls, that's not going to affect the average number of phone calls that they would expect to get in the next hour. So if for some reason 1 hour they got 30, they're not going to expect to get, 50 the next hour or less or more. It's just if the average is 10, then they expect to get 10, for example, right? So what is the Poisson distribution? What's the probability mass function here? Okay. This one I'm going to have to give us the distribution here, the formula. It's a little bit harder to think about the intuition of it in the scope of what we're covering in this course as an introductory level. So we're just going to want to make sure we're comfortable using it and try to get a feel for situations that fit a Poisson process. So the Poisson distribution We use P for Poisson. Getting X events, we have two parameters, lambda T, which is kind of like an upside down Y. That's the Greek letter lambda. I don't know if we've come across that yet. Lambda, lambda times T there. All right. So the probability of observing X values within a given time period is equal to e to the negative lambda T times lambda T to the X power divided by X factorial. This is good for X equaling 0, 1, 2, yada, 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 goes on up, countably infinite. So what do we have in this? We have T and lambda. So in here, lambda is the average number of outcomes per unit time. The average number of outcomes per unit time. So it might be like, we know that on average, this office gets 10 phone calls per hour. Lambda would be 10 there. Per unit time. T then would be the number of units of time, right? T is the number of units of time that you're going to have. T would be the number of units of time. All right. Something that's kind of nice about the Poisson distribution, then the expected value of X is just lambda times T, and the variance of X is also equal to lambda times T, which is kind of a neat result. And the expected value of X, we'll take a look at an example, and I think you'll see that just with the verbiage, intuitively, it makes sense that that would be the average because, or the expected value, because the problems usually state what an average number of events that you would expect to see. So it's almost a little redundant in some aspect. So this is the Poisson distribution here. That would be the Poisson distribution. Box around that. Bingo. Okay. All right. Okay, so we have that. So we have our lambda T times X. So we'll take a look at some examples here shortly about how to work with the Poisson distribution here. This is exactly the probability that you get X events occurring in that unit of time. We also have a table. This is our second table, if you've been watching these videos in order, that we're being exposed to. So in the back of our textbook, this is table A2, but it's a pretty common probability table of cumulative values. Gives values of the CDF, cumulative distribution function, right? So that's the probability that you get less than or equal to some number of events R. This is just the sum of the Poisson probabilities, parameter lambda T. X goes from 0 all the way up to R events. X goes from 0 all the way up to R events. Also useful as well. And so let's just go ahead and take a quick glance at what that table looks like here. Textbook, let's go to the back. Tables and proofs. And we're going to go paging through. So there's our binomial sums, cumulative probability of our binomial sums. Got a few pages of this. And then usually next we'll see we get a table for the Poisson probabilities. There we go. All right. And so in the table, mu is lambda times T. And so that's our expected value or expected number of events per time. And so, yeah, we'll take a look at that. Notice the parameter here, right? This is X semicolon mu. Mu is lambda times T in the table. Px comma mu, and what we have here is P of X comma lambda T. So mu would be lambda T in the table. I guess I'll just notate that here, right? Mu is equal to lambda T. Mu is equal to lambda T. All right. We need to look at an example here. We need to look at an example. and work with this computation. The Poisson distribution, it's got factorials, exponents, it's got e in it. Might look kind of messy, but it's really not that bad to work with. It's actually kind of nice to work with. So let's just take a look at an example here. Let's say that during a lab experiment, the average number of radioactive particles, the average number of radioactive particles passing through a counter in 1 millisecond. 1 millisecond is 4. What is the probability that 6 particles pass through the counter in a given millisecond? What is the probability that 6 particles enter the counter in a given millisecond? All right, so we're going to work, this is exactly 6. We're looking for exactly 6, so we can use our Poisson distribution that we have in the top box there. What we need to know is we need to know what lambda is, we need to know what t is, right? So let's see here. So lambda is the average number of outcomes per unit time. What is the average number of outcomes per unit time? It says that the average number of particles passing through the counter in 1 millisecond is 4. So it is 4 per millisecond, right? 4 per millisecond. So our unit of time here is 1 millisecond. So for t, in our event, how many units of time are we considering? Well, we're looking at just a single given millisecond. In a given millisecond, that's just 1 millisecond, 1 unit of time. So lambda t is 4 times 1 there. And we are concerned with getting exactly 6 particles. We are concerned with exactly 6 particles. So you want the probability that x is equal to 6 when lambda is equal to 4 and t is equal to 1. So let's plug that in. This is e to the negative lambda t. So this is e to the negative lambda t. So negative lambda would be negative 4, and t is 1, so that's negative 4 times 1, or just negative 4 in your exponent. And then it's lambda t to the x. Lambda t to the x. So that's going to be times, lambda t is 4 here. The x power then, this is 6. We're looking for 6 particles. So e to the negative 4 times 4 to the 6th divided by x factorial. Divided by 6 factorial. And so we need to run that computation through our calculator. E to the negative 4 times 4 to the 6th divided by 6 factorial. Almost all of these questions we're going to be rounding off to 4 decimal places. And so I've got about 0.1042. Please do check your calculator skills. Make sure you can agree and get the same 4 digits. 0.1042. 0.1042. All right. There we go. Looks good. So there's that first example. You get a feel for how this works. Let's do one more. Suppose the number of people entering a movie theater, suppose the number of people entering a movie theater averages 1 every 2 minutes. Averages 1 every 2 minutes. 1 every 2 minutes. So using the Poisson distribution, Poisson. Find the probability at least 4 people enter. Find the probability at least 4 people enter during the interval 12 to 12:05. 12 to 12:05. All right, let's take a look at what we have here. Suppose the number of people entering a movie theater averages 1 every 2 minutes. Using the Poisson distribution, find the probability at least 4 people enter during 12 to 12:05. Okay, so what are the parameters that we have here? What is lambda? Lambda is the average number of outcomes, expected number of outcomes per unit time. So in this case, we're given what? They average 1 person every 2 minutes. 1 person every 2 minutes. So 1 every 2 minutes, that would be a half per minute, right? A half per minute. 1 every 2 minutes. A half per minute. Or, well, yeah, let's think about this. We could do this in 2 ways. So you could do this in 2 ways. You could say your unit of time is a minute. And then what is t going to be equal to? T, this is a 5-minute interval. 12 to 12:05, that's a 5-minute interval, right? So you can do that. And then lambda t is 5 times a half, that's 2.5. Or you have some wiggle room on how you want to set up your parameters. What if I say that my unit of time is 2 minutes? Then lambda is 1, but my unit of time, it's 1 per 2 minutes. So then when t, remember t is counting the number of units of time. So in a 5-minute interval, how many 2-unit times do we have? In a 5-minute interval, well, you have 2 minutes, 4 minutes, then an extra minute, which is half. So if your unit of time is 2 minutes, then t is 2.5. T is 2.5. I think it's a little bit awkward to do it this way because if you're thinking unit of time, it's nice for things to be like a 1, right? But there's nothing wrong with your units being 2 minutes as long as you adjust t appropriately, right? It's 2.5 2-minute time intervals. Either way, you look at what lambda t is, 1 times 2.5, it's still, lambda t is still 2.5. And so when we plug this into our Poisson distribution, lambda t is still going to appear the same. It's still going to be 2.5 everywhere. So what do we want to answer in this question? We want to know what's the probability at least 4 people. At least 4. So 4 or more. All right. When we see that greater than symbol, hopefully our complement flags are being raised. X can go up onto infinity technically, so we have to look at the complement event. The complement of 4 or more in the discrete case. In the discrete case, it would be 3 or less, right? X is less than or equal to 3 because I'm not going to have 3.5 people enter. So 1 minus the probability that X is less than or equal to 3, right? Here we go. So we have this. So you can compute this probability in 2 ways, right? You could do this in either by looking at the probability that X is equal to 0 or 1 or 2 and just do all of those by hand. Or we can just use the table. And I highly prefer we use the table here. Definitely want to get used to using the table. So let's see what this is going to be. This is 1 minus. What's the probability that X is less than or equal to 3? So we have that lambda t is equal to 5 or 2.5. Lambda t is equal to 2.5. Let's find 2.5 on the table. Here we go. Mu 2.5. And then less than or equal to 3, R would be equal to 3. So I'm looking at right there, I believe, 0.7576. 0.7576. And 1 minus that is 0.2424. And that is our answer for this question. All right.